Hello there. It's good to share this quiet with you. Let the room settle around your breathing, like a blanket that remembers your shape. Tonight we'll cradle a curious idea, something scientists whisper about at the edge of gravity's deepest well. Black holes have a rumored twin, a dark, quieter sibling called a gravastar. Picture a star that collapsed, but didn't quite fall through. Instead of a point of no return, there's a thin, tense shell holding back a strange interior pressure from the very fabric of space, keeping the doorway closed. Light comes close, slows, then turns away. Nothing shrieks, nothing breaks, just a poised hush where an abyss might have been. We'll take this slowly, like moonlight slipping across a floorboard. What a gravastar is, why some physicists propose it, and how it might change what we think the night is made of. This is a working theory, gentle and careful, perfect for drifting. If this soft journey brings you ease, a quiet like and a calm subscribe. Help others find their way here too, only if it feels right. For now, let your breaths lengthen, your shoulders loosen, and your thoughts move like distant tides. The dark twin waits, and we'll meet it together. Lift your eyes to the quiet sky and imagine each point of light with a secret heartbeat. Most are steady, ordinary suns, patient as kitchen clocks. A few live faster, burn hotter, and end with a kind of suddenness that shakes the surrounding night. When those heavy stars run out of fuel, the warmth that once pushed outward like a gentle breath fades away. Gravity, which has been waiting politely, steps forward. The core caves in on itself in less than a second. A hush falling so swiftly that the outer layers stumble and then rebound as a supernova brighter than the galaxy that hosts it. A brief lighthouse seen across millions of years. After the glitter, something remains. A remnant with its own weather of gravity, time, and light. For many stars, the ending sits on familiar shelves. If the core is modest, packed neutrons lock arms and build a neutron star, a city-sized ember with a mass like the sun, crust stiff as steel, magnetic fields that comb space. If the core is heavier, the collapse runs downhill without a path back up, and we speak of a black hole, a region so curved that all roads lead inward. A horizon around it like a shoreline no swimmer can cross from the wrong side. Those two endings usually cover the tale. It's comforting when nature keeps tidy books. Yet not all stories accept a single closing paragraph. In the spaces where theory stretches, another possibility has been proposed. A third shelf, narrow and mysterious, labeled with a word that feels like a whispered spell, Gravastar. Picture the collapse again, but slow it down in your mind until each moment becomes a bead on a string. Pressure climbs, temperature rages, the core squeezes tighter than any substance we've ever held. In the traditional picture, that squeeze never ends. Mathematics points to a singularity, an infinitely small, infinitely dense point, wrapped by an event horizon. The horizon is not a wall, it is a boundary in space and time, where light's last chance slips away. Cross it, and the future narrows to a single direction, in. The trouble is not with the poetry of the idea, but with its bookkeeping. Infinite numbers are clues that a theory has walked beyond its map. Many physicists accept black holes as real, while still feeling the itch. Surely the world has a way to complete the story without dividing by zero. The Gravastar proposal answers that itch with a gentler turnout in the road. Instead of the core shrinking forever, the collapse triggers a phase change, not like water boiling on a stove, not like ice forming in a glass, but something more fundamental. The fabric of the vacuum itself, The background hum that quantum physics says is never truly silent takes on a new state. Empty space is not empty. It carries energy even when no particles are present. Usually that energy is spread thin, a faint, even mist. Under collapse, according to the Gravastar idea, that mist condenses. Imagine compressing a cloud until it becomes a lake, then a bead of dew, then a single shining drop that refuses to be smaller. The interior becomes a pocket of vacuum energy with a peculiar personality. It pushes outward. In the language of cosmology, it acts like dark energy, a negative pressure that resists compression and encourages expansion. That push does not explode the star. It meets gravity's pull and holds. Between the outward insistence of the vacuum core and the inward loyalty of gravity, a balance forms that is not brittle but taut, like a drumhead pulled smooth across a frame. Around the core, the theory places a shell thin beyond ordinary imagining. Perhaps no thicker than an atom, yet strong, the way a diamond is strong when the lattice is perfect. Here the matter may behave as a single coherent wave, a state with a family resemblance to a Bose-Einstein condensate, where many particles share one quantum rhythm. In a laboratory, such condensates appear only near absolute zero, colder than any night on Earth. The shell in this picture would also be cold, a stillness that helps the structure hold its shape. It would be under tension the way the skin of a bubble is under tension, but with a ferocity that numbers struggle to capture. Stretch it an eyelash, and you would need the might of mountains. From far away, the differences fade. Space curves around the object as though a black hole were present. Starlight grazing past it bends and takes a longer path. Gas falling toward it spins into a hot disk that glows in X-rays and radio waves. If it turns, it drags space along, twisting the paths of nearby photons like a slow whirlpool. Point a telescope, and you would see darkness ringed by light, a shadow against the glow. In many tests, a gravastar and a black hole would wear the same costume, and our instruments would nod, unable to convict either one. This is part of the idea's charm and its challenge. It preserves the successes of black hole physics while replacing the troublesome singularity with a well-behaved interior. Yet a small difference, like a hidden seam in a perfect suit, might be there. A black hole's horizon is a one-way door with no surface to strike. The story ends at the boundary. A gravastar, without that horizon, would have an outer layer you could, in principle, touch, if touching were not instantly fatal. Matter plunging inward would not vanish across a point of no return. It would meet the shell. That meeting could be quiet or bright, depending on the details. Some models suggest a whisper of heat would leak out as the shell digests what falls in. Others allow for faint echoes in gravitational waves, small after pulses, following the main ring that forms when two such objects merge. Our detectors listen for such murmurs now, sifting the noise for patterns that repeat with a shy delay. The absence of a perfect horizon also softens a famous paradox about lost information. If there is a surface, even a strange one, information might leave in altered form rather than being edited out of the universe altogether. The interior has its own mood. Where a black hole's core is a question mark, the gravastar's center would be a region similar to what cosmologists call de Sitter space, a dome of constant energy density that encourages expansion. But the shell holds the line. The outward push inside and the inward pull outside meet at that razor-thin boundary and make a truce. Time passes differently near the shell. Clocks there, if clocks could survive, would run slow compared with clocks kept in a quiet room far away. Light climbing out loses energy, sliding to redder colors, the way a ball loses speed rolling uphill. To an external observer, any flicker from the shell would be stretched and softened by gravity's patient fingers. It helps to anchor the picture with familiar scales. Take an object with the mass of our Sunday. Its event horizon as a black hole would sit at about 3 kilometers from the center, smaller than a city. A gravastar of the same mass would be almost the same size from the outside. The shell would hover just above that radius, separated from the would-be horizon by a distance so small that light could walk it in a heartbeat of a heartbeat. For heavier objects, millions or billions of solar masses, like the giants at galactic centers, the numbers balloon, yet the proportions keep their poise. The shell remains incredibly close to where the horizon would have been, the difference measured not in everyday meters, but in units that feel like a secret margin inside the math. There are quieter signatures to consider. If material falls steadily, a black hole accepts it without complaint, hiding the details behind the horizon and letting only the disk announce itself. A gravastar might glow faintly from the surface, a low ember smeared by extreme redshift, so dim it would look like darkness wearing a soft scarf of warmth. The image a radio telescope stitches an orange ring like the one made famous by the Event Horizon Telescope would be almost the same for both, because that ring comes largely from light bending, not from the surface itself. The difference hides in subtleties, how quickly the brightness changes, how the polarization of the light twists, whether there is a tiny excess in certain frequencies that would hint at a place where infalling matter lands. Spin complicates the dance in gentle ways. Most compact objects rotate, some with the pride of a skater pulling arms in, turning faster and faster. Rotation creates an ergo region around a black hole, a place where space-time's swirl is so strong that nothing can stand still. A gravastar with spin would swirl space too. Somewhere between the shell and the sky, there might be a similar region where energy can be coaxed out of the rotation, like a hand brushing power from a water wheel. If two such objects merge, the final ring down, the dying tone of space-time as it settles could, in certain models, carry a hint that the interior is elastic rather than absolute. The tone would be nearly the same, but the fading might contain that soft, delayed echo, a repetition like the room answering after your voice stops. Beneath the storytelling is a simple motive: kindness to the laws of physics. Singularities ask us to ignore the rules at exactly the moment we need them most. A gravastar replaces the infinite with the extreme but finite, a move mathematicians and engineers both appreciate. The vacuum energy inside is not a free invention. It borrows its character from the same phenomenon that appears in cosmology when we talk about the universe's accelerated expansion. The shell's coherence is not fantasy. We make matter march in step in laboratories, letting atoms share a single wave in traps, cold enough to make breath fog seem tropical. Extrapolating those ideas into a collapse is bold, yes, but not reckless. It asks for a new balance of forces rather than a bullet through logic. There's a humility worth keeping here. Gravastars are still a hypothesis. The equations can be made to behave. The numbers can be coaxed into consistency. The diagrams can be drawn without tearing the page, but nature gets the last vote. Our telescopes grow more patient, our detectors more attentive, our modeling more careful. Each improvement shrinks the hiding places where differences can live. If the universe has built gravastars, it seems to have done so with the faintest fingerprints, timing that runs a hair off expectation, light that leans a fraction to one side, waves that end with a soft, delayed breath. It helps to remember why the question is worth the candle. At the end of a massive star's life, matter, pressure, and space-time write their closing lines together. Whether the final word is horizon or shell, singularity or vacuum core, the process teaches how gravity and quantum rules share a roof. If the Gravastar idea is right, the vacuum isn't just a backdrop, it steps onto the stage. If it's wrong, the search still sharpens our tools and tidies our habits of thought. Either way, the night becomes more legible. Hold the picture. A star collapses, heat and pressure climb, and instead of falling into bottomlessness, the center ripens into a region that pushes outward. A thin, strong layer forms a quiet boundary with the world. Space curves, light bows, matter swirls, and from afar it wears the mask of a black hole cut so cleanly, even a careful glance might pass it by. Inside, the script is different. No infinitely sharp point, no place where the math throws up its hands. Only a tense, balanced stillness, like a breath, held not in fear, but in poise. From that balanced picture, one small but decisive difference comes into focus. A Gravastar would have a true surface, a physical shell, exotic, yet still matter not, a purely mathematical boundary that swallows every path, and a surface can answer. It can hold a memory of what arrives, let energy settle, and speak back in a whisper instead of erasing the conversation. Where a horizon says no return, a shell says leave a trace. Those traces, the faint, late-time echoes in gravitational waves, the slight, delayed glow when hot gas meets a boundary, are where an observer might follow the thread and tell the two dark twins apart, even when a hurried look would see only one. That small shift soothes an old worry that has haunted black hole physics for decades, the information paradox. Quantum mechanics treats information like a kind of bookkeeping. The universe refuses to lose. The tally may shuffle, but it doesn't vanish. A classical black hole seems to break that promise, hiding anything that crosses the horizon and tossing the ledger into the fire. If a Gravastar stands where a black hole would stand, there is no singular point and no one-way edge. The story that falls in does not disappear. It threads itself into the shell and the smooth interior, encoded in how that surface stretches, warms, and hums. The page isn't burned. It's pressed like a leaf between glass. Do such objects truly exist? The honest answer is gentle and plain. We don't know. No telescope has pointed to the sky and said, beyond doubt, that is a Gravastar. It may be that nature never chooses this route. Even so, the mathematics sits comfortably beside the laws we trust, and anything that fits there deserves attention. The trouble is that, from far away, a Gravastar wears almost the same face as a black hole. Space warps around it in much the same way. Gas falling toward it heats, brightens, and seems to vanish at nearly the same radius. The silhouette against a glowing background, the soft coin dark shadow, would look nearly identical. To tell them apart, we have to lean on subtleties, the way you tell a lullaby from a distant train, only by how the last note fades. One place to listen is in gravitational waves, the ripples in space-time raised when heavy things move and merge. When two black holes collide, the fabric rings in a pattern we've learned to recognize with instruments like LIGO and Virgo. If two Gravastars were to embrace and become one, the ring down might not be perfectly smooth. A true horizon is a perfect absorber. It ends the song cleanly. A physical surface can reflect just a little. That reflection could send tiny echoes back into the wave, faint and delayed, like the last reverberation in a quiet church after the choir has stopped. Teams have searched patiently for such hints. A few analyses have seen glimmers at the edge of what our detectors can trust. Others find only silence. The verdict sleeps for now, and that is fine. Bedtime stories can hold a question without rushing it. Even if the sky never grants us a gravastar, thinking about one is not wasted breath. It reminds us that extremes might have more than one answer, that collapse can end in balance as well as surrender. It nudges our instruments to be kinder and keener, better at catching the long tail of a wave, the late glow of a surface, the way a boundary holds heat. And it points softly toward the larger puzzle that keeps physics honest. How to let general relativity, the language of curved space and heavy things, speak clearly with quantum mechanics. The language of small, lively fields. Singularities are where their voices tangle. A finite, well-behaved interior, like the one a gravastar imagines, is a sketch of harmony. Not proof, just a lantern held up to the path. While that thought rests, it helps to hold something we know is real and near: neutron stars. They are cousins, born in the same bright violence that can leave a black hole in its place. When a dying core isn't quite heavy enough to tumble past the brink, the fall stops on a different shelf. Protons and electrons are squeezed together until neutrons become the ordinary citizens of a very strange city. The whole thing is only about 12 miles wide, the size of a town ringed by highways, yet it can weigh more than our Sunday. It spins like a skater, with arms pulled in, and its gravity presses so intensely that any visitor would be flattened to a film only atoms thick, long before a thought could form. Try a more homely picture. Imagine a teaspoon, the small one you'd stir into tea. Fill it with matter from the heart of a neutron star and ferry it to Earth. On a scale, it would press down with the weight of a mountain range about 1 billion tons packed into that sugar-sized scoop. Numbers like that are hard to feel, so we lean on metaphors that breathe. This is matter near the limit of how close particles can sit without losing themselves. Under the thin skin of a neutron star is a crust nuclei, arranged in a crystalline lattice, something like metal, but so tight that the word solid feels too soft. Dip below, and the crowding grows fierce. Nuclei begin to change shape, pulling into rods, flattening into plates, corrugating into labyrinths. Physicists, forgiving and a little amused, call this nuclear pasta. The names are playful. The reality is profoundly orderly. Geometry appears because it is the most comfortable way to be cramped. Deeper still lies a sea where individual identities blur. Neutrons flow in a superfluid that slips without friction, quiet as fog sliding through a valley. Protons, fewer in number, can line up into a superconducting web that pins magnetic fields into thin, quantized threads. Everything is stiff and delicate at once. When the star's crust catches and then relaxes, the whole body can twitch, and the spin jumps by a whisper tiny glitches that astronomers have watched for years. The lighthouses we call pulsars beam radio pulses as they turn, so regular that they keep time almost as well as our best clocks. With enough of them spread across the sky, their slow collective sway lets us feel gravitational waves that take years to crest, the bass notes of the universe's long music. In the company of neutron stars, the gravastar idea feels less lonely. Both are messages written at the edge of what matter can bear. One finds balance in quantum pressure and nuclear forces, stopping the fall on a ledge carved by the Pauli exclusion principle, the quiet rule that keeps identical fermions from sharing the same state. The other, if nature allows it, would settle by turning its interior into something smooth and softly repulsive, then drawing a shell so tense and thin it holds the shape like a drumhead tuned to the last turn of the key. Each is a way the cosmos says, enough, not with a wall, but with a hammock stretched, resilient, and strangely peaceful. That difference isn't just philosophy, it changes what the night sounds like when we listen closely. An object with a surface can respond, a place without a horizon can remember. Information doesn't vanish into nowhere. It settles into structure, into pattern, into heat that comes and goes on a timetable we might with patience measure. When two dark bodies collide, that difference could add a faint tail to the ringing. When hot gas dives inward, it could leave a late, breath-soft glow. None of it is loud, and that is exactly why it's useful. Astronomy thrives on the almost missed, the slight delay, the barely brighter trace that tells us where to look again. Whether or not Gravastar ever becomes a catalog entry, the effort to find its footprint sharpens the senses we carry into the dark. The known and the possible begin to rhyme. Neutron stars give us something we can time, weigh, and model with care. Gravastars give us a gentle mirror to hold beside black holes, a way to ask whether the universe prefers edges or skins, horizons or shells, surrender or equilibrium. Between those choices, the night stays kind. It rewards slow questions and steady hands. It reminds us that even at the limits, especially at the limits, nature loves a balance that holds. And since balance is the heart of the comparison, it helps to feel how one side of it works from the inside out. Deep in a neutron star, pressure doesn't simply press, it insists. Neutrons crowd so tightly that an ordinary atomic nucleus begins to seem spacious by comparison. Toward the center, where temperature is fierce and density climbs beyond imagination, our confidence thins. The inner core may set aside familiar identities and let quarks mingle freely in a quark-gluon sea, a brief echo of the universe's first moments when everything was hot, quick, and undivided. Or it may choose more delicate arrangements, droplets, lattices, or pockets where strange quarks join the dance structures we can name with careful equations but have never held in any hand. This is the ledge where neutron stars find their enough, quantum rules, and the strong force knitting order at pressures that would undo anything else, turning the star into a clock, a lighthouse, and a laboratory all at once, our anchor while we keep listening for the softer echoes that might belong to its darker twin. The same severity shapes the magnetism. A compass behaves on Earth because our planet wears a modest magnetic cloak. A typical neutron star wraps itself in a field 1 trillion times stronger, and a magnetar winds that strength another 1,000-fold tighter. Fields like that do not sit politely on the surface. They thread the crust, stress it, and when the tension slips, they snap the way sea ice splits with a gunshot. The star jerks, the field reconfigures, and radiation erupts a starquake, bright enough in high-energy light to be felt across the galaxy. Under those conditions, atoms are stretched into needles, and the vacuum itself becomes a little different, as if the field teaches empty space a new trick for how light should pass. Rotation adds its own rhythm. Some neutron stars whirl hundreds of times each second, steady as a drum, beaten by a patient hand. Their magnetic axes rarely line up with their spin, so beams bloom from the poles and sweep the sky like lighthouse bars. If our world sits in the path, the beam brushes us on every turn, and we receive a pulse as regular as breath in sleep. These pulsars keep time with a devotion that humbles clocks. The best of them wander by microseconds over years, letting astronomers use their beats to navigate in thought, triangulating positions in deep space, or to listen for gravity's slowest waves. The long swells raised by giant black holes turning together in distant galactic cores. The road to these discoveries began with doubt. In the 1,930 seconds after neutrons were found, theorists speculated that a collapsed star might be supported by the stubbornness of quantum rules. The idea sounded too strange to many. Then, in 1967, a young researcher, Jocelyn Bell, watched a recorder lay down ink and noticed a whisper of regular ticks that no storm or machine explained. The signal, repeated with uncanny precision. For a tender moment, the thought of distant senders, little green messengers, was allowed to sit on the table. Soon, more sources arrived from different corners of the sky, all too numerous and well-behaved to be artifice. A new class of object had announced itself.
A soft
The prize that
whisper
followed did not
of
include
relief.
Belle Burnell's name, a decision that still feels off-key, yet her quiet diligence remains the first note in the melody. Neutron stars are not only metronomes, they can be matches struck in the dark. Paired together in a tight orbit, they leak energy through gravitational waves, their dance shrinking, their steps quickening, until at last they meet. The collision is a layered spectacle. Space itself rings. Our detectors feel that ringing as a rising chirp and a fading sigh. Light bursts across the spectrum. A kilonova blooms a transient glow, powered by the decay of newly forged elements. Jets may spear outward and, if pointed our way, flash as short gamma-ray bursts. For a few days, the remnant shines, as if a small piece of night turned to ember. Then it cools, leaving behind a heavier object and a trail of enriched debris. From those debris fields comes a connection to our daily lives. In the crush and heat of the merger, free neutrons bombard seed nuclei, sticking so quickly that elements climb the periodic ladder in a sprint called the R process, rapid neutron capture. When the storm calms, the unstable products transmute toward stability, releasing light as they settle down. In that settling lies the birth of gold and platinum, of lanthanides that color the kilonova's glow, of iodine that one day will thread through bodies and tides. The ring on a hand, the contact in a car's exhaust system, the medicine that lights an image inside a clinic, each is a cooled memory of two collapsed stars folding together long before humans learned to smelt. If neutron stars are the firm limit we can point to, they may still not be the last word in density. There is room, perhaps, for an intermediate kind of compact star. The idea of a quark star begins with the pieces inside protons and neutrons. Quarks come in flavors up, down, and stranger varieties with gluons carrying the binding between them. Under ordinary conditions, quarks are confined. Pulling one apart from its partners only hardens the tether, like stretching a rubber band that thickens as you tug. But if you squeeze matter hard enough, confinement may give way. Neutrons could dissolve. Quarks might roam more freely in a collective sea. A star made mainly of that sea would be smaller for the same mass, its gravity tighter, its skin a sharper cliff. Such a star could be layered. The outermost miles might mimic a neutron star's crust nuclei in a lattice, electrons skimming like a thin cloud. Beneath, a mixed region might carry both neutrons and quark matter in patterns that change with depth. At the heart, quarks could move as a uniform fluid. Magnetic fields could become even more stubborn. Thermal light might escape differently. The whole object would sit between the stiffness of nuclear matter and the smoothness of quark matter. a compromise that the universe might choose in some cases and not in others. Among the possibilities, one carries a special lure: strange quark matter. Besides the familiar up and down quarks, the strange quark can join the blend. Some calculations suggest that, at the right density, a mixture of up, down, and strange quarks could be more stable than ordinary nuclear stuff, so stable that a droplet of it, once formed, would prefer to stay as it is. If true, small strangelets might wander the galaxy, and a whole star of such matter could be the quiet champion of endurance. It remains an if, handled carefully. Experiments on Earth reach high temperatures for an instant, coaxing quark-gluon plasma into existence at accelerators, but they cannot bottle the cold, crushing pressure of a star's center. Observations lend clues: unusual masses and radii, glitches and bursts, cooling rates that hint at unfamiliar processes, but no single signature has stepped forward to claim certainty. The not knowing is its own kind of gentle. We learn by laying constraints like stones in a path, narrowing what could be true. Pulsar timing traces mass and size with exquisite care. X-ray spectra measure hotspots and atmospheres, sketching the gravity at the surface.
What is your greatest dream?
Gravitational waves weigh and probe the stiffness of matter during merger, turning the last orbits into a ruler that measures compressibility. Each method speaks softly on its own. Together they build a chorus that raises or lowers the chances for quark cores, for strange matter, for shells and transitions. In this quiet, the shared theme is balance. Neutron stars ask the strong force and the strict manners of quantum identity to hold the line against gravity's insistence. Magnetars add the stern geometry of magnetic fields to the bargain. Pulsars layer rotation on top, turning their whole bodies into resonant instruments. If quark stars exist, they would be a deeper truce still. Confinement eased not by heat, as in an accelerator's flash, but by pressure, the slow, relentless squeeze of a collapsed sun. Each configuration is nature's way of answering the same question: how close can things be without letting the story tear? The images help. Picture a city of neutrons whose streets are etched by magnetism, crustal plates sliding by millimeters and jolting the skyline. Picture beams that sweep like a lighthouse over a calm sea, and a clock that keeps time faithfully from 1,000 light years away. Picture two such cities merging, avenues colliding and rebuilding, and in the dust a sparkle of new elements that will one day live in rings, wires, and salt. Picture, too, a deeper city we may never see, a place where quarks stroll freely, and strange is simply the normal word. Let those pictures fade to silhouettes. The science doesn't have to shout. It leans on regular pulses, on slight delays, on the color of a fading ember after a stellar storm. It invites patience and rewards it with understanding that lands softly. When the mind grows quiet, the extremes feel less harsh, more like steady hands holding the edges of the night, making room for stars to be born, to burst, and to leave behind objects that hum, flicker, and ring good company for a long, restful breath. From that calm ledge, one daring idea steps forward: the strange matter hypothesis. It whispers that, at great density, a mixture that includes strange quarks could be even more stable than the matter we know. If so, contact might be contagious. Touch ordinary material with a tiny nugget, a strangelet, and the neighborhood could quietly rearrange itself, atom by atom, into the steadier pattern. From a distance, it reads like science fiction. Up close, it earns a seat among serious possibilities because the math and the models don't forbid it. The the reassurance comes with the risk. If such droplets exist, they should be vanishingly rare, and their handshake with everyday matter exquisitely faint. Most would pass through Earth like ghosts in fog, leaving barely a rumor in their wake. In that balance, the boldness of the idea and the gentleness of its likelihood, the universe carries both the thought and the comfort in the same steady hand. With that in mind, some astronomers look again at compact stars we think we know, and wonder if a few are quark stars wearing neutron star clothing. The differences would be quiet ones: a mass just a bit too large for a given radius, a cooling curve, a shade too quick or too slow, a tremor in the spin that doesn't fit the usual script. As our instruments learn to read finer lines, better timing arrays, sharper X-ray eyes, wave detectors that feel the last shiver of a merger, we may learn to tell which heart beats with neutrons and which with freer quarks. Draw the focus back from extremes and let the gaze rest on something humbler and more common, the way a fire settles into coals. That is the role of white dwarfs in the stellar family. Most stars, including our sun, will end their bright years not in a roar, but in a slow unfurling. After the core exhausts its hydrogen, the star swells into a red giant, breathing outward until it may graze the orbits of inner planets. Then the puffed-up layers drift off, shaped by light, into a delicate planetary nebula, a glowing shell that looks like a blossom thrown onto night. What remains at the center is a white dwarf, small as a world, heavy as half a sun, and bright because it is hot, not because it makes new fire. The trick that holds a white dwarf together belongs to quantum rules rather than heat. Electrons refuse to share the same quantum state. It's a quiet insistence stitched into the fabric of matter. Pack them close and they push back, not by moving faster from warmth, but by needing new states to occupy when the old ones are taken. That push is electron degeneracy pressure, a mouthful of a phrase for a very simple idea. When there's no room left in the lower seats, the audience has to climb the balcony, and the climb creates pressure. Gravity leans, quantum rules brace, and the result is a compact ember the size of Earth with the density of 1,000,000 oceans. Left alone, a white dwarf has no engine. It shines because it's hot and slowly cools over billions of years, an ember dimming until, far beyond the current age of the universe, it would become a black dwarf, cold, dark, and quiet. But many are not left alone. In a close pair, a white dwarf can pull gas from a companion star. That gas swirls down, layers itself on the surface, and when enough hydrogen piles up, it ignites in a brief runaway flame. A nova flares bright, sudden, and survivable for the dwarf, which then goes back to gathering more material, patient as a tide. There is a sharper threshold, though, an upper limit to how heavy a white dwarf can be. Add mass, either by steady feeding or by merging two dwarfs, until the total approaches about 1.4 times the sun's mass, the Chandrasekhar limit, and the quantum stool the star sits on is pulled away. Electrons can't supply enough pressure. The core collapses, and in that plunge, carbon and oxygen fuse in a runaway that unbinds the star completely. A Type Ia supernova blossoms with a brightness so consistent that it serves as a yardstick, helping astronomers measure distances across the deep. By comparing how bright these explosions appear with how bright they truly are, we learned that galaxies are not only receding, but doing so faster and faster. A discovery that gave a name, dark energy, to a new, pervasive push in the cosmos. It's natural, after walking among alternatives and cousins, to turn to the object that haunts the center of many of these stories. Black holes are the stern answer to gravity's favorite question: how far can you go? When matter is driven past every other defense, beyond electron degeneracy, beyond the neutron's stubbornness, past any pressure we currently know how to calculate, the fall continues until the mathematics points to a singularity, a place where density is not just large, but undefined. Around that center forms the event horizon, the border where escape would require outrunning light itself. Cross it, and every possible path tips inward. Time and space trade roles in a way that sounds like a riddle and behaves like a law. From the outside, black holes live in a spectrum of sizes. The stellar kind, born from collapsed stars, weigh a few to a few dozen suns. In galactic hearts sit supermassive black holes, patient giants with millions or billions of solar masses, shepherding stars and gas in orbits that take centuries to trace. Between them lies a quieter class, intermediate mass black holes, harder to catch in the act, hinted at by dense star clusters and off-center X-ray sources. And in the far reaches of theory sit primordial black holes, tiny ones that might have formed in the early universe, if density fluctuations were sharp enough, still unconfirmed, still tempting in the way unsolved puzzles are. They may sound like endings, yet even here the night keeps its gentleness. An event horizon is not a wall, it's a promise about paths. Light skims and bends, drawing rings and crescents around a backlit hole. Hot gas spirals and flares before slipping across the edge, painting time with flickers our Earth-spanning telescopes can watch. When black holes merge, space-time rings like bronze, and our instruments feel the tremor. When matter feeds them, we learn how magnetic fields twist, how beams take shape, how jets are launched. These aren't just finales, they are laboratories where gravity speaks most fluently. Set this beside the quieter possibilities we've held: white dwarfs keeping their balance, pulsars keeping the time, magnetars storing storms, the soft maybes of quark stars, and the unsettling elegance of strange matter, and a theme appears. Nature prefers equilibrium when it can, but it doesn't flinch at the cliff when the path leads there. Some stars rest on quantum rules. Some push those rules until new phases emerge. Some continue to a horizon that keeps its own counsel. And because the universe is generous, each fate leaves a trace. A cooling ember, a ticking beam, a sudden flare, a patient glow, a perfect ring. Let the mind hold a few small scenes. An Earth-sized white dwarf shining blue-white against a nebula it once breathed out like a sigh. A nova, quick as a gasp, then quiet. An old pulsar sweeping a beam a traveler could steer by. Two compact stars meeting and minting gold in their parting light. A black hole's silhouette against a hot, swirling backdrop. The curve of space turning into shape. None of these speak loudly. They're bedside stories the cosmos tells at the pace of breath, guiding us toward how matter chooses to end, to rest, or to fall. And if we lean closer to the darkest stage, time itself changes key. Near a black hole, it behaves like a careful musician notes stretched near the stage, while the balcony keeps steady time. Walk toward deep gravity, and your own clock slows compared with clocks far away. It's not a feeling so much as a relationship between places. Watch someone fall from a safe distance, and the scene thickens, each heartbeat longer than the last. Their colors slide to red, then into darkness, as light loses energy climbing out. For the traveler, there's no drum roll at the edge, no sign, no spark. The horizon is crossed in finite time, calmly. Only deeper in do tides grow fierce, a pull so uneven it would draw a body into strands. Spaghettification sounds playful, but it names a serious fact. Gravity is not the same at head and feet, and near a hole's heart, that difference becomes destiny. In this way, the two threads join traces we can follow on the sky, and the quieter rearrangement of time itself, each teaching the same lesson in a different voice. Black holes are not perfectly silent, at least in theory. Quantum fields near the horizon flicker, and where those fluctuations meet gravity's edge, a thin glow appears, Hawking radiation. It is faint for stellar and supermassive holes, far too faint to measure, yet so the giants darken on timescales that dwarf the age of the universe. Tiny, hypothetical black holes would behave differently. The smaller the horizon, the hotter the glow, ending in a brief, bright, final breath. That glow complicates a long-standing promise physics tries to keep. Information should not be destroyed. Hawking radiation looks almost featureless, a thermal fog that seems to forget what fell in. The black hole information paradox lives in that forgetfulness. Many possible reconciliations have taken their turn on the chalkboard. Black hole complementarity proposes that no single observer sees rules broken. To someone outside, information never quite crosses. To someone falling, nothing special happens at the edge. The holographic principle goes further, hinting that every detail inside might be perfectly encoded on the horizon's two-dimensional skin, the way a pattern on glass holds an entire scene in a new language. None of this is bedtime dogma. It's a working truce that preserves quantum honesty while respecting gravity's geometry. We've aimed eyes the size of Earth at the darkness to test what can be tested. The Event Horizon Telescope stitched radio dishes across the globe into one patient instrument and focused on two familiar giants, the supermassive black hole in M87 and the quieter one at our galaxy's center. The result was a soft ring wrapped around a dark interior light, bent into a crescent by motion and gravity, a shadow larger than the horizon itself, because paths curve so strongly nearby. Those images don't show the hole, they show matter just outside it, glowing as it falls. Even so, they match general relativity with a grace that earns a calm nod. The predicted size, the shape, the degree of asymmetry, where the accretion flow races toward us and brightens all there. Black holes also act as governors in the grand machinery of galaxies. Nearly every large galaxy shelters a supermassive one at the core, and the mass of that central object tracks the properties of the surrounding bulge. Like a duet, grow one, and the other tends to answer. Feed a black hole, and the falling gas heats, shines, and sometimes launches jets that spear outward at near light speed. Those jets can clear out gas, throttle star formation, or compress clouds and encourage it, a feedback loop that sculpts where and when new suns appear. The darkest engine becomes an architect, not by touch, but by influence. Widen the frame, and the cosmic web comes into view. Clusters and filaments, voids and sheets. A lace of matter formed by gravity's long patience. Two unlit partners dominate this landscape. One is dark energy, a gentle pressure that accelerates expansion. The other is dark matter, which gathers structure. Together, they hold roughly 95% of the universe's budget, leaving all the stars, planets, and glowing gas to share the remaining 5. The names are humble, dark, as in not directly seen, placeholders for phenomena we know by their effects. The trail to dark matter began with motions too fast to be comfortable. In the 1,930 seconds, Fritz Zwicky measured the Coma cluster and found galaxies moving as if more mass were binding them than the eye could find. Decades later, Vera Rubin mapped how stars circle inside spiral galaxies. If visible matter were all that mattered, outer stars should slow, the way Neptune orbits more slowly than Earth. Instead, rotation curves flattened. The outskirts moved almost as quickly as regions nearer the center. The simplest reading is an unseen halo extending well beyond the luminous disk, holding stars in their swift paths. Independent clues keep pointing the same way. Light from distant galaxies bends around intervening mass, and the strength and pattern of that lensing often require more gravity than starlight accounts for. Colliding clusters, like the bullet cluster, separate normal matter, which slams to a halt and heats, from most of the mass, which sails through, suggesting the dominant component barely interacts, except by gravity. The ripples in the cosmic microwave background, the universe's afterglow, carry a harmonic fingerprint shaped by how much ordinary matter, dark matter, and radiation were present when the first atoms formed. Read that spectrum carefully, and you again find a universe where dark matter outweighs the familiar by about 5 to 1. What it is remains open in a welcoming way. It doesn't shine, absorb, or scatter light. It passes through ordinary matter with disinterest, if at all, except for the pull of gravity. Many physicists favor the idea of new particles born in the early universe. WIMPs, weakly interacting massive particles, would be heavy and aloof. Axions would be feather-light and numerous, rippling like a field rather than a gas of individual travelers. Experiments wait underground and under mountains, shielded from noise, hoping to feel a rare tap on a detector. Telescopes watch for gamma-ray whispers where dark matter might annihilate. Cavities with exquisitely tuned microwaves listen for axions converting to light. So far, the answer is an ongoing silence that tightens the constraints and sharpens the questions. There are also bold attempts to adjust the rulebook instead of adding new players. Modified gravity theories argue that the laws we use work splendidly in the solar system, but need a nudge on galactic scales. Mund-modified Newtonian dynamics changes how acceleration relates to force at very low accelerations. And with the right choice of parameters, it can fit rotation curves with striking economy. The challenge comes when all the evidence is considered together. Clusters, lensing maps, the microwave background, the growth of structure over time. Any alternative must satisfy this full orchestra, not just one instrument. And the harmony is hard to maintain without something very much like dark matter returning to the score. The other invisible partner, dark energy, enters through distance and time. Type Ia supernovae, those white dwarf detonations with consistent peak brightness, serve as standard candles. In the late 1,990 seconds, surveys reading their light at great distances found something unexpected. Rather than slowing under gravity's mutual pull, galaxies were receding faster and faster. Whatever fills space has a small, persistent tendency to push space apart. In Einstein's equations, that push can be modeled as a cosmological constant, a uniform energy of the vacuum. It might be that, or it might be a field that evolves, or it might be that gravity itself needs a deeper rewrite. For now, the constant fits the data with quiet efficiency, while the deeper reasons linger like a soft question at the end of a page. Edges and encodings keep returning like a quiet refrain. Time slows in strong fields because geometry bends. Horizons appear because paths curve until outward no longer exists. Faint quantum light leaks because uncertainty allows brief, paired stirrings at a boundary. Galaxies keep their swiftness because halos hold them. The cosmic web grows because non-luminous matter provides a scaffold. The universe accelerates because emptiness carries a peculiar weight. None of this asks for alarm. It invites patience. The instruments we build, dish fields spread over continents, interferometers that read distances smaller than atoms, cryogenic detectors waiting in stone, are simply careful ways of asking simple questions. Hold for a breath, a few scenes under one sky, near a black hole, a clock that runs slow, and a ring of light curling around a darkness larger than itself. Farther out, a spiral whose outer stars refuse to lag, steadied by an unseen halo. On the largest scales, a lattice of clusters stretching for billions of light years, while empty spaces swell gently as dark energy does its quiet work. Their strangeness has a logic. They are extraordinary without being chaotic. They hum with rules steady enough to fall asleep beside. And yet good rules still leave room for challenges at the edges. Modified gravity ideas earn respect for their nerve and for the puzzles they try to solve. Some versions sketch galaxy rotation curves with elegant economy, then stumble on the microwave background's fine ripples, or on how light bends around clusters. So the broad reading stays simple. Unseen mass does most of the scaffolding. Even so, those alternative sketches keep curiosity awake, reminding us that honest science always keeps a spare chair for dissent, and that the sky, patient as it is, will decide which story holds when all the notes are heard. Another quiet partner shapes the story more deeply still. In the late 1990 seconds, teams measuring distant Type Ia supernovae expected to confirm a slowing universe, gravity dragging on expansion, the way brakes slow a rolling cart. The measurements came back with a softer, stranger answer. The expansion was speeding up. Something in the fabric of space behaves like a steady pressure, nudging distant galaxies apart a little more each day. We call that something dark energy, not because it is brooding, but because it does its work without light. This pressure seems to belong to space itself. As space grows, the effect doesn't thin out. There is simply more of it, so the push accumulates. Add up the universe's budget, and this term dominates. Roughly 68% dark energy, about 27% dark matter, and only 5% the familiar stuff of stars, planets, and people. The most conservative explanation is a cosmological constant in Einstein's equations, a uniform vacuum energy that never tires. He once labeled the term a blunder when he thought the cosmos was static. The expansion made the constant seem unnecessary. Now the expansion's acceleration gives that old symbol a second life, though likely not for the reason he imagined. Here the mathematics grows bold, interpreting the constant as vacuum energy connects to the same idea that appeared in Gravastar interiors. Empty space is not truly empty. Quantum fields hum, even in their quietest state. But when theorists try to compute how much energy that hum should carry, the tally overshoots reality by an absurd factor, 10 to the 120th power, an error so grand it has become a cautionary tale. To soften that mismatch, some suggest a dynamic field nicknamed quintessence, whose energy changes over time. Others wonder whether gravity itself needs a gentler rewrite on the largest scales. The way forward is observational patience, mapping how the expansion rate has changed across cosmic history, tracing the growth of structure, and comparing many lines of evidence until one picture sits most comfortably with all of them. Answers about the most extreme objects are tied to answers about the beginning. Roll the universe backward, and temperatures rise, distances shrink, and distinctions blur. About 13.8 billion years ago, everything we can see and all that supports it was packed into a hot, dense state where familiar forms could not stand. In the first sliver of time, matter was a bright plasma of quarks, gluons, leptons, and photons, too energetic for atoms or even nuclei to exist. As expansion eased the pressure and lowered the temperature, quarks paired and tripled into protons and neutrons within microseconds. A few minutes later, those nucleons fused into light nuclei, mostly hydrogen and helium with a dash of lithium, setting the initial chemical mix for future stars. Electrons still wandered freely then, scattering photons so often that space behaved like frosted glass. Only after roughly 380,000 years did the air clear. Temperatures fell enough for electrons to settle into orbit around nuclei, making the first neutral atoms. Photons decoupled and began traveling mostly unhindered, their wavelengths stretching with expansion, until that ancient light now reaches us as a cool, nearly uniform microwave glow. The cosmic microwave background is a baby picture with astonishing clarity. Its tiny temperature variations, only about 1 part in 100,000, carry a fossilized map of conditions when the first atoms formed. That near uniformity hides a riddle. Regions on opposite sides of the sky have never been in touch since the beginning. There hasn't been time for light or anything else to run a message between them. Yet their temperatures match to uncanny precision. How did such distant patches agree on the same conditions? Why are there so few relics of high-energy defects that some early universe models would have painted across the sky? Standard Big Bang evolution alone can't tidy all of that. A brief, astonishing growth spurt provides the missing grace note. Cosmic inflation proposes that, in the universe's first heartbeat of time, the scale factor doubled again and again, some 60 e-foldings or more, in a duration so short that words struggle to hold it. A small, smooth region could then expand to cover everything we can now observe, ironing away wrinkles and spreading uniformity like a neatly pulled sheet. Quantum fluctuations during that phase, tiny, random tremors in density and field values, were stretched from subatomic scales to astronomical ones. When inflation ended, those tremors became the seeds of structure. Slightly denser places pulled in more matter, slightly thinner places gave some back. Over hundreds of millions of years, the seeds grew into stars, galaxies, and the filaments that lace the sky. The fingerprints of this story appear in multiple places. The microwave background's pattern of hot and cold spots has a characteristic spectrum, more power at certain angular scales, a series of peaks and troughs matching the expectations of sound waves ringing in the early plasma, with amplitudes set by the proportions of ordinary matter, dark matter, and radiation. The large-scale distribution of galaxies echoes those same harmonics, a faint, frozen ripple known as baryon acoustic oscillations that serves as a standard ruler for cosmic distances. The agreement across these measurements is a quiet triumph. Independent data, same tune. What drove the initial rush? A simple model uses a scalar field, the inflaton, perched high on an energy landscape. While the field rolls slowly, its nearly constant energy density acts like a temporary cosmological constant, powering rapid exponential expansion. When the roll steepens and the field tumbles, inflation ends. The field's energy converts into a hot mix of particles and radiation in a process evocatively named reheating. From that point on, the universe follows better-known rules: cooling, combining, collapsing where perturbations were strongest, lighting the first stars, and letting chemistry and time do what they do best. These ideas are bold but not untouchable. Experiments and surveys keep score. Polarization patterns in the microwave background may reveal the faint swirl of primordial gravitational waves, a direct signature of inflation's violence. Galaxy redshift maps grow deeper and wider, tracking how structures form and drift. Supernova distances, lensing surveys, and the timing of pulsars weave independent checks on the same history. The plan is modest and ambitious at once. Accumulate gentle, precise measurements until the early minutes and the present acceleration are stitched together by a single tasteful seam. There is a resonance, too, with the objects that drew us here. Vacuum energy shows up in more than one costume, as a hypothesis inside Gravastar interiors, as the cosmological constant that keeps expansion accelerating, as a stand-in for whatever field might have driven inflation and then retired. Quantum fluctuations write the first lines in the pattern book that galaxies later embroider. Gravity, with its habit of bending time and shepherding light, translates those lines into the structures we see. The same equations that sketch horizons around black holes also guide the growth of the cosmic web. The same insistence that information matters animates debates about the horizon of a hole and the horizon of the observable universe. Think of it like a quiet score played on different instruments. In the early universe, the theme is speed, space, stretching so fast that nearby becomes far apart before there is a second breath. In galaxies, the theme is structure halos, holding stars in swift orbits, and funnels feeding central engines. Around black holes, the theme is boundary light, curving into rings, time dilating, quantum fields whispering at the edge. Across it all, dark energy keeps a soft pressure on the tempo, coaxing the beat a little quicker as ages pass. None of this needs to feel harsh in the telling. The numbers are large, the spans long, but the logic is gentle. Observations do not shout, they nod, cross-check, and settle into agreement one decimal place at a time. When a model strains, it yields the stage. When an idea survives, it does so because the sky keeps repeating the same story in different accents. The work is patient, the instruments careful, and the night, despite its strangeness, remains a companionable place to rest while the universe goes on, unfolding its steady, intricate design. Far beyond this quiet room, the cosmos continues with patient purpose, and the far future waits like a shoreline we can sketch, but not yet walk. The path ahead depends on what dark energy truly is, and how the geometry of space keeps its accounts. If the gentle push that speeds expansion remains steady, as observations currently whisper, then space will go on stretching forever, and the stretching will quicken with age. Galaxies outside our local group will slip beyond our observable horizon, not by outrunning light through space, but because the space between us and them keeps lengthening. Skies owned by astronomers in distant eras will hold only a handful of nearby companions. The rest of the universe will be present, but unreachable, like a story remembered only by its first page. Star-making continues for eons. Gas clouds cool, collapse, and ignite. New suns rise from old debris. Gradually, the pantry runs low. The easy fuel thins. The last stars to burn are small red dwarfs, thrifty engines that glow for trillions of years. When even these embers fade, the scene simplifies. Stellar remnants become the common furniture. White dwarfs cooling into crystalline monuments, neutron stars slowing their clocks, black holes shepherding the dark with nothing but geometry. The drama softens into endurance. Quantum rules keep a faint fire alive, even in that endurance. White dwarfs radiate away their heat and harden. Some will crystallize until the whole object is a diamond the size of a world. Isolated neutrons decay, though inside a star they are held fast. Protons might be mortal too. No one has witnessed their departure, but some theories permit a decay time so long it requires towers of zeros. After the era of stars passes, black holes take the stage. Near their horizons, quantum fields flicker, and from that flicker arises Hawking radiation too faint for us to catch now, yet relentless across unimaginable spans. A black hole, born from a star, needs roughly 1067 years to evaporate. The giants at galactic centers can persist until around 100 years. Even they will end, not with a roar, but with a final warm breath of particles and light. What remains after the last horizon dissolves is almost nothing, and almost everywhere. A universe vast beyond analogy, thin as a thought, filled with a sparse soup of photons, relic neutrinos, and a few light particles drifting through an endless dusk. Temperatures rest a hair above absolute zero. Entropy approaches its ceiling. Interactions become rare. Differences fade. This is the dark era, often called heat death, not a defeat, simply the settled state of a cosmos that has shared and mixed until no further work can be done. Another fate is more dramatic. If dark energy's pressure strengthens with time rather than staying constant, expansion could become a kind of insistence that tears bonds once believed unbreakable. First galaxy clusters loosen, then galaxies unspool, planetary systems are unthreaded, orbits empty. In the final chapters, stars, planets, and even atoms would be pulled apart as the fabric stretches faster than forces can hold. This big rip would arrive at a finite time in the future if the equation of state slips past a critical value. Current measurements do not demand that path, but the possibility stands as a reminder that the unknown can still edit the script. There is a mirror image as well. If dark energy weakens or reverses, and matter's gravity proves sufficient, expansion could slow, halt, and turn around. Distances would shrink. The cosmic microwave background would warm from microwaves through infrared to visible to ultraviolet and higher. Structures would crowd, collide, and dissolve into a tightening blaze. The whole universe could fall back toward a state like the beginning of a big crunch. In some models, that is not an end but a hinge, leading to a big bounce and a new expansion, a cosmos that breathes on timescales beyond simple comfort. For now, the quiet verdict from many lines of evidence: supernova distances, the ripples stamped in galaxy distributions, the fine texture of the microwave background, is a nearly flat cosmos whose expansion is accelerating in a way consistent with a cosmological constant. That reading points toward the long, cool future of endless expansion. Yet humility is part of the method. Dark energy remains more label than understanding. Better maps, longer baselines, and new instruments may reveal structure in what currently seems smooth, or hint at a field that changes mood over time. Across these distant fates, the characters met along the way retain their meaning. Gravastars remain a careful possibility, a way to imagine equilibrium in places where we wrote infinities. Neutron stars show that quantum rules can balance gravity for a while. They're lighthouses sweeping out clocks that rival our best machines. Dark matter holds halos and sculpts the web. Dark energy widens the stage under every act. Inflation lifts quantum whispers into the first seeds of structure. Black holes translate curvature into boundaries that time and light respect. From equations that contemplate singularities to detectors that hear the ring of merging horizons, the universe offers laboratory and lullaby in the same breath. The speed of our learning is almost as startling as the subjects. Within a century, the picture widened from a Milky Way imagined as everything to a cosmos of uncountable galaxies. Expansion moved from idea to measurement. Pulsars stepped from theory into metronomes drawn on chart paper. Black holes went from inference to images of crescents and shadows built from a planet-sized array. Gravitational waves, once a thought experiment, arrived as brief chirps plotted on screens. The large-scale structure emerged as a lace of filaments and voids. Each advance settled one question and uncovered several more questions that feel sharper, kinder, and better aimed. What is dark matter made of? Why does dark energy's push have the small, persistent value it seems to possess? Do gravastars or quark stars condense from real collapses? Or are they teaching tools that refine our detectors? Even if nature prefers other solutions, what happens where classical equations draw a singularity? Does a deeper theory soften that point into a smooth interior, the way ice becomes water when pressure and temperature shift? Which path will reconcile quantum rules with curvature, strings, and extra dimensions, loops that quantize geometry, or a new idea that makes today's options look like drafts? Uncertainty here is not a flaw, it's an invitation. Science narrows wide possibilities into manageable ones, replacing sweeping maybes with small, testable claims. A favored model is not a throne, but a chair at a table where data are served repeatedly. When the sky declines to answer quickly, we build better instruments, pose cleaner questions, and wait with purpose. The process is patient by design. The questions we keep are the ones that survive contact with measurement. Future work follows the same rhythm. Telescopes map deeper and finer structures, tracing how galaxies settle along filaments and how voids empty. Interferometers listen for weaker and longer gravitational waves, reading the stiffness of matter in the last orbits of a merger and the sway of space itself over years. Surveys chart supernovae across time to see whether the acceleration has always worn the same expression. Quiet detectors buried in rock continue to reach for a rare nudge from dark matter. Each instrument is a new sense. Together, they form a body capable of noticing subtleties no single tool could catch. Even the far futures fold back into the present in small, humane ways. The crystals imagined inside ancient white dwarfs are kin to the order in a snowflake. The timing of pulsars refines our clocks. The jets from black holes light up gas that will one day seed new stars. Gravitational lensing, a massive arc drawn by curvature, helps us weigh clusters and map matter we cannot see. The microwave background old light, cooled to a whisper, still carries the harmonics of sound waves from a plasma that existed before any star was born. Everywhere, echoes connect scales and eras. In the same spirit, a few scenes settle easily behind the eyes. A sky in a far epoch, sparse but precise, where a handful of companion galaxies share the night while all others have slipped beyond reach. A white dwarf cooling into a planet-sized diamond, black and perfect under no sun. Two neutron stars clasping in a last orbit and forging gold in their parting glow. A black hole's ring, light, dragged into a crescent by speed and gravity. A graph traced by a detector in a quiet lab. A tiny chirp that announces a collision half a universe away. None of these moments are loud. That is their strength. They are measured, repeatable, and stitched to one another by rules that are gentle to state and deep to explore. If the universe ends in thinness and quiet, the story we tell about it remains a source of warmth. The value is not only in the answers, but in the habit of listening carefully and refining the questions. A century ago, many of these ideas would have sounded like bedtime fantasies. Today, they rest on measurements, cross-checked by independent routes, carried by instruments people built with patient hands. Tomorrow's instruments will be subtler. Tomorrow's questions will be wiser. The progress is not a sprint down a single corridor, but a slow widening of hallways, each opening into another room you didn't know the house contained. This is what makes the Enterprise feel companionable. The night is large, its futures many, and yet the rules are reliable enough to trust. Gravity bends time. Quantum fields never quite sleep. Information demands to be accounted for. Energy follows ledgers we can audit. Within those rules, there is room for surprises, room for a Gravastar to be real or to remain a clarifying idea, room for dark energy to be constant or to move, room for a deeper theory to turn a singularity into a smooth interior. The possibilities are not a cause for worry. They are the landscape of discovery. Here, where curiosity and calm meet, it's possible to rest. The universe will carry on, stars born and spent, horizons meeting and parting, light stretching into longer colors. Our role is to notice, measure, compare, and tell the truth as well as we can. That work has its own comfort. It gathers the strange into the familiar without sanding away the wonder. It leaves us with a night that is still dark, still vast, and nevertheless kind, steady enough to fall asleep beside, generous enough to wake to with new questions, and patient enough to hold every careful answer we manage to earn. Each generation of observers inherits a sky already in progress, picks up the thread, and stitches a few more quiet truths into the tapestry. The strange, compact, and luminous objects we've cradled tonight mark the edges of what matter and geometry can manage. They prove that reality tolerates forms far wilder than common sense would permit, while still obeying equations that sit neatly on a chalkboard. The surprise is not that the universe is odd. The surprise is that its oddness is so methodical. From those methodical surprises comes the habit of continuing, of asking softer, better questions, and building instruments gentle enough to hear the answers. Somewhere in the data waiting on hard drives, there may be a faint afterbeat in a gravitational wave ringdown, the kind of echo a surface would return if a Gravastar truly replaced a horizon. Upgrades now running through detectors, the A+ improvements to ground-based interferometers, the growing networks that triangulate signals across hemispheres are teaching us to notice what used to blur. A space-based observatory, LISA, will one day feel the long, low notes from massive black holes merging and from compact binaries slowly spiraling over years. That new register could reveal late-time structure that ground detectors miss. Pulsar timing arrays, timing dozens of millisecond pulsars with microsecond fidelity, have already started to map a background hum at nanohertz frequencies. If an echo hides anywhere, patience like this is how it will be found. The particle behind dark matter might be shyer still. Some experiments rest miles underground in cold, immaculate rooms, waiting for a single heavy visitor to nudge a crystal lattice. Others, a generation of axion haloscopes, sweep tunable microwave cavities through frequencies where axions, if they are out there, could convert into photons with a click too faint for human ears, but not for superconducting amplifiers. Cosmic surveys weigh the universe by how it warps light. Lensing maps from instruments like the Rubin Observatory's wide-field camera will trace the scaffolding dark matter provides across time. Cross-checking particle searches with astronomy's quiet bookkeeping, every non-detection is not a failure. It is a trimmed branch, bringing the target closer in. The dream of a complete theory of quantum gravity, one that lets quantum fields and curved spacetime share a grammar, also advances in a measured way. On one front, holographic dualities keep finding new footholds, strongly coupled quantum systems that behave as if they live on the boundary of a higher dimensional, gravitational world. On another, loop-inspired approaches try to quantize geometry itself, turning areas and volumes into discrete spectra so that singularities smooth into finite cores. Neither path owns the high ground. Both earn their rations by explaining and predicting pieces of the same puzzle. Meanwhile, observations test the edges. Polarization patterns in the cosmic microwave background may carry the faint curl of primordial gravitational waves. High-resolution images of black hole environments check how closely real spacetime follows the metrics lines. Precision timing of pulsars constrains how gravity radiates and how spacetime ripples carry energy away. Imagination stays on a leash, but the leash is long enough to reach into the dark. It's reasonable to picture objects that hold information rather than erasing it. Compact stars with surfaces that ring and skins that store a memory in their vibrations. It's plausible that there are phases of matter available only under compressions found inside dying suns. Color superconducting quark matter, where quarks pair the way electrons do in a metal's superconducting state, or crystalline phases that lock a pattern into the densest interiors. Space could have regional habits, cosmic domains where fields take slightly different vacuum values, leaving small discontinuities at their borders. Time already flows at different rates in gravitational wells. On the largest scales, different expansion histories may exist in separate pockets of a broader multiverse. These are not claims. They are careful invitations to devise tests. Evidence for larger structures keeps refining. The cosmic web filaments, nodes, and voids reflects the tug-of-war between gravity and expansion and the pressure of the early plasma's sound waves. Baryon acoustic oscillations leave a faint preferred scale in galaxy distributions, about 500 million light-years today, a yardstick we can compare in different eras. Sunyaev-Zeldovich effects let us see hot electrons in cluster gas, imprint shadows on the microwave background. Weak lensing distorts the shapes of distant galaxies by 1% or 2%, average over millions, and the pattern of shear sketches the invisible mass. None of these alone would convince. Together, they behave like witnesses, telling the same story in different accents. Even the near void between galaxies is not truly empty. Quantum fields flicker there, and those fluctuations, while canceling in aggregate, shape how forces behave at small distances. Casimir experiments two metal plates in a vacuum, attracting because the quantum vacuum between them supports fewer modes of vibration, demonstrate that emptiness has structure. In cosmology, the vacuum's energy density if treated as a cosmological constant, acts like a soft spring in Einstein's equations, pushing on the scale factor with quiet persistence. The mismatch between naive quantum estimates and the tiny value inferred from astronomy remains a warning that our counting is off by a comical margin. That warning steers theory as effectively as a measurement would. More speculative thoughts earn their place when they suggest checks. A dark matter planet would not shine, but it would still pull. Precise transit timings or microlensing surveys could flag objects with mass, but no light. If there are compact quark stars, their mass-radius relation should differ slightly. X-ray pulse profiles from hotspots swept across by rotation let us solve for both mass and radius with percent-level accuracy, using light bending and Doppler boosting as tools. If strangelets are possible, cosmic ray searches can look for unusual charge-to-mass ratios. Collider environments probe the hot version of deconfinement, while astrophysical observations constrain the cold, dense version. Instruments coming online extend the senses in directions that suit this quiet hunt. The next Event Horizon Telescope upgrades, sometimes called the NGEHT, will add stations and widen frequency coverage, sharpening our view of the rings and crescents around black holes and letting us watch those shapes evolve on the timescale of orbits close to the speed of light. CMBS-4, a future stage of microwave background experiments, will measure temperature and polarization with astonishing depth, constraining neutrino masses, counting light relics, and pushing on inflation's remaining wiggle room. Atomic clocks compared over long baselines can test whether fundamental constants drift with time or vary with location. So far, they do not. To exquisite precision, P. Ptolemy and related projects dream of catching the cosmic neutrino background, the leftover neutrinos from the first seconds of the universe, using tritium targets chilled close to absolute zero. If a spectrum kink appears where theory says it should, the early universe gains another direct photograph. It's tempting to declare a destination, the detection of a specific particle, the proof of a specific compact object, the selection of one quantum gravity among many. The practice is humbler. Each discovery has tended to open a door rather than close one. Galaxy redshifts birthed the expansion. The expansion demanded dark energy. Dark energy raised questions about vacuum energy and inflation. Inflation ran headlong into quantum gravity. Pulsar timing revealed neutron star interiors. Those interiors pointed toward phases of matter beyond nuclear physics. Mergers revealed where gold originates and how stiff matter is at twice nuclear density. Gravitational wave astronomy began with stellar mass black holes and now points towards space-based detectors that will listen to the slow bass of supermassive pairs. The pattern is not a staircase with a top. It is a spiral inward, tightening around the heart of how space-time and quantum fields share a world. Speculation expands in a controlled way. Consciousness as a physical process clearly exists in the universe. Brains are arrangements of matter, obeying the same equations as stars. But whether observation plays a role in cosmology beyond how measurements are made is an open, philosophical edge. What cosmology can test are correlations and distributions. If something as grand as a multiverse leaves a statistical fingerprint, say, a particular distribution of vacuum energies in habitable domains, then careful surveys and anthropic reasoning may meet halfway. Until then, the discipline keeps the boundary between poetic curiosity and testable claim clear, without losing any of the wonder. The same discipline governs talk of time that branches or loops. General relativity already permits unusual topologies and closed time-like curves in certain solutions, but to be physical, those solutions must respect energy conditions and quantum stability. Quantum mechanics, for its part, allows superpositions and entanglement that muddle naive ideas of chronology. Where they meet, in proposals about baby universes budding off from black holes or bounces replacing Big Bang singularities, the touchstone remains the same. Does the idea offer a calculation that could, in principle, differ from a rival and meet the sky again in the data? Meanwhile, the ordinary, extraordinary continues. White dwarfs cooling into planet-sized crystals, their cores settling into ordered lattices as heat leaks into space. Magnetars, storing energy in twisted fields and releasing it in flares that jolt detectors across Earth. Jets from accreting black holes, carving radio lobes, hundreds of thousands of light years wide. Their edges glowing where they ram into intergalactic gas, gravitational lenses stretching and duplicating the images of background galaxies, sometimes delaying one image by days so that we can watch the same supernova explode twice. Each of these is a proof that the universe has a patient engineering department and that our tools are finally good enough to appreciate the workmanship. All the while, human timescales remain tender compared with the ages involved. The long futures of heat, death, or bounce and return will not touch a single morning here. What they give, instead, is proportion. Knowing that stars exhaust their fuel, that horizons leak, that information may be conserved in forms we barely recognize, takes the sting out of not knowing and replaces it with a kind of trust. The rules are discoverable. The parts talk to each other. The ledger balances even when we haven't learned every line item yet. Picture the sky with that trust in place. Gravastars as a possibility, filed under echoes to check. Quark stars as a possibility, filed under mass radius curves to sharpen. Dark matter as a certainty about gravity's bookkeeping. With the identity of the bookkeeper still under investigation, dark energy as a constant for now, a question mark for later. The work is the same, whether the answer lands next year or next century. Build the instrument, cancel the noise, measure twice, and keep a spare hypothesis on the coat rack by the door. Perhaps the universe is not only stranger than imagined, but kinder to careful imagination than feared. When a signal appears that cannot be fit, the moment won't mark an ending. It will be the beginning of another circle in the spiral, the way the first pulsar was, the way the first ringed silhouette of a black hole was, the way the first chirp of merging horizons was. A new pattern will be named, a new equation written, a new instrument planned. The textbooks will change their diagrams, and sleep will be as easy as ever, because the method remains. Ask gently. Test what can be tested. Admit what cannot. And when the night stretches wide, remember that you are a witness in a universe that rewards attention, where even the faintest echo, caught cleanly, can turn a whispered maybe into a new piece of the truth. Imagine tools that feel less like machines bolted to rockets and more like senses grown directly into the sky. Today we loft mirrors and antennas, counting photons and timing pulses with careful code. Tomorrow's observatories could be braided into space-time itself, arrays that don't merely watch, but join the rhythm, the way a stethoscope learns a pulse by touching skin. Think of kilometer-scale atom interferometers, where falling clouds of ultra-cold atoms become rulers for gravity's softest tremors. Think of spaceborne laser triangles that hold formation over millions of miles, measuring distances to the width of a molecule and catching the long, low notes from massive black holes turning together far away. Magnetic fields already lace galaxies. Instruments may one day hitch a ride on those lines, reading Alphen waves and plasma eddies across light years, like a spider senses motion in its web. Deep beneath ice and ocean, neutrino observatories can widen their nets for particles that cross a light year of lead, as if it were fog. On the ground, new interferometers tune for quieter floors, watching the ring down of a merger long after the first shout, searching for faint overtones that tell us how the horizon settles. In orbit, constellations of small telescopes could fly in formation as a single, shape-shifting eye, sliding its baseline to sharpen detail on demand. Some probes might feel more like materials than vehicles. Swarms of programmable matter, micron-scale craft that rearrange mid-flight could adapt to radiation belts, coronal storms, or the thin drag of alien skies, reweaving antennas and mirrors the way a school of fish changes shape. Metamaterials might bend light just so, turning star shades and coronagraphs into scalpels that tease out the breath of an exoplanet from a billion times brighter starlight. Cold atom gyroscopes, quiet as dew, could anchor navigation where star fields blur. Quantum-limited amplifiers would listen for a single axion turning into a photon in a tuned cavity. A click too faint for any ear, but not for a superconducting circuit chilled near absolute zero. Borders tempt imagination most. It's easy to picture sensors stationed close to horizons, listening for quantum whispers, where geometry tightens, even if the tides there would turn metal into mist. The thought is still useful. A craft that skims the photon sphere could stare into a hole's mirror, watching light circle the drain and return, its spectrum telling how space-time curls. Elsewhere, solar sails and laser sails trade fuel for patience, drifting outward, on pressure alone, the way seeds ride a breeze. Interstellar dust becomes a data set, the heliopause, a laboratory, the magnetic drape around our sun, a lens to bend radio waves into new images. Travel may shift from speed to geometry. The equations already allow tunnels where effective distances shrink. The engineering arguments that warn us away are stern, but precise. Even without shortcuts, we can fold the problem, cryogenic hibernation for instruments, and one day, perhaps for people, closed-loop ecologies that sip rather than burn. Onboard AIs that learn to notice on the way, steering telescopes toward the unexpected. A fleet could leave slowly and arrive clever. Senses will not be hardware alone. The brain is a physical system, wet, electrical, quantum, only in the ordinary way. Yet it becomes a formidable pattern detector with training. Radiologists learn to see edema as quickly as you read your name. Musicians hear a key change before a single note declares it. With feedback from simulations and sky data, perception can become a partner to code, recognizing lensing arcs, pulsar glitches, or exoplanet transits as a kind of music. Neuroadaptive interfaces might let experts tune a detector in real time, aligning attention with anomalies as they bloom. It isn't magic, it's biology, aligned with signal. Whole worlds can become instruments. Seismometers scattered across Mars and synchronized by laser links could turn the planet into a single ear for meteor strikes and for the whisper of its core. A radio array on the moon's far side, shielded from Earth's chatter, could listen to the cosmic dark ages when the first atoms met and the first stars had not yet lit. Ground observatories, helped by adaptive optics and machine learning, already cancel atmospheric shimmers so thoroughly that air becomes almost as steady as space. Hypertelescopes braid light from small mirrors into larger apertures. Formation flyers promise to carry that braiding into orbit. Many tools will arrive as side effects. A cargo tug that nudges asteroids becomes, with a better accelerometer, a gravimeter mapping rubble interiors. A starshade, built to photograph Earth-like worlds, turns into a lab for exozodiacal dust and the choreography of debris rings. In-orbit servicing extends telescope lifetimes long enough to track seasons on the same exoplanet, to see wind patterns shift over years, to catch a volcanic bloom in reflected light. The engineering of longevity becomes a science of time. As methods refine, quiet channels sound louder. Polarization reveals magnetic order where we once wrote off chaos. Spectroscopy reads chemistry in starlight, pixel by pixel, measuring winds and rotation in worlds we will never touch. Timing takes another step. Pulsar timing arrays stitch a galactic interferometer that hears waves with year-long periods. Atom interferometers on balloons and in orbit bridge ground and space bands. Lunar laser ranging keeps testing gravity's crispness as clocks reach 18 decimal places of agreement. A planet's gravity measures as a tiny difference between two ticking hearts. A gravitational wave becomes a small change in the rhythm of a million-mile laser arm. With every gain, the line between observing and participating blurs a little. A detector gentles the field it measures. A mirror warms and shapes the air around it. A formation flying array writes geometry into the sky. The goal isn't domination, it's tuning, using resonance and coherence the way a violin uses its hollow body to strengthen a note. The craft of science becomes less a sweeping spotlight and more a duet, instrument, and score, learning each other's intentions. The universe has been speaking all along, in ripples of space-time, in neutrinos that left a supernova before its light could fight free, in polarization that remembers which way photons were last scattered, in magnetic storms that pull curtains of aurora across polar skies. Fluency grows as our alphabet widens. Quieter interferometers will push past vacuum hiss until merger aftertones and horizon physics separate cleanly. Dark matter experiments will trade targets and thresholds, from germanium crystals to superfluid helium, from heavy candidates to feather-light axions. Radio arrays will map neutral hydrogen across cosmic time, tracing how the first stars switched the universe from dark to bright. Quantum networks will teleport states across satellites and cities, anchoring time and linking telescopes into single instruments that span the Earth. It helps to hold a few grounded pictures amid the daydreams. A starshade pedaled tens of meters wide flies tens of thousands of kilometers from a space telescope so that together they cancel starlight and show a planet a billion times fainter, its color wiggling with clouds and ocean. A laser link measures changes between spacecraft to picometers, feeling a gravitational wrinkle glide by. Two optical clocks compare ticks across a continent. From the tiny difference in their rates, we read how Earth's gravity slopes between them, turning time itself into a surveying tool. A superconducting qubit in a dilution refrigerator listens for a single microwave photon created by an axion. A nanowire goes resistive the moment one arrives, a yes, no in the quiet. None of this guarantees a particular prize. It guarantees clarity. If a Gravastars echo hides in ringdowns, better timing and models will either find it or fold it back into horizon physics with gratitude for the lesson. If dark matter prefers to be a light field rather than a heavy particle, resonant cavities and haloscopes will make that introduction. If inflation left a curl pattern in the microwave sky, patient polarization maps will either show it or set limits that steer theory away from the wrong valleys. Each result, even a null, narrows the room where truth can sit. The work stays gentle, even as the tools grow bold. Mirrors, lasers, clocks, crystals, antennas, superconductors, plain things, arranged with taste. A radio orchard on the lunar far side. A ring of satellites passing quantum states like notes in a round. Seafloor strings that watch for upgoing blue flashes when a neutrino finally collides. Formation flyers drawing baselines across the night. The list sounds technical. The feeling is human. These are new senses, not ornaments. A wider truth threads through all of this. Curiosity isn't a light we shine on a mute stage. It's one way the stage hears its own acoustics. When an analysis sharpens, when a detector settles to its noise floor, and a hidden line steps out of the background, that moment is the cosmos answering in a dialect we learned by practicing. The sky overhead was never a ceiling. It remains an invitation, clearer as instruments grow quieter, as questions grow kinder, as patience lengthens. Stand outside, and the stars still look like pins on velvet. Behind that comfort, an instrumentarium is assembling. Spaceborne interferometers will listen to the bass. Ground-based giants will feel the tenor. Pulsars will keep metronome time. Optical clocks will make maps from differences in ticks. Axion searches will sweep dials through nights of silence. Lunar arrays will lean into the hush before the first dawn. Somewhere in those notes, a new harmony waits. A faint echo where a surface should be. A spectral line from an ocean around a far star. A kink in a spectrum where a light relic lives. A hiccup in time where gravity and quantum rules shake hands without shouting. The next steps are not louder, just finer. Cancel a little more noise. Cross-calibrate one more way. Let instruments learn from one another. Ask questions that can survive being asked twice by different methods. Build in room for surprise. The unknown is not receding. It's pacing us, setting a tempo just ahead. That isn't failure. That is the essence of discovery. We move forward not by demanding grand finales, but by welcoming small, repeatable crescendos. And if there is one lesson the night keeps repeating, it is that we are not bystanders. We are part of the apparatus by which the universe comes to know itself, and our attention is a mirror the world uses to see its own structure. Even the faintest signal, caught cleanly, can turn a whispered maybe into a new piece of truth. Engines will help. Equations will help. But the quiet strengths, care, patience, tenderness with data carry us just as far. The sky is wide. The tools are readying. The invitation is open. Close your eyes. Listen for the small notes and feel how the dark hums back. The story of the universe is still being written, line by slow line, and curiosity is the ink that doesn't run dry. Someday, someone will look back at this era, the way we remember the first fire kindled in a cold cave as the moment the dark became legible. Mirrors on mountaintops, radio dishes sewn across continents, clocks that keep time to 18 places past the decimal, interferometers tracing distances smaller than an atom. These are our torches. They brighten a night so vast it could swallow thought. Yet every spark reveals something intimate. The cosmos is not out there, separate and aloof. It threads through us. The calcium in teeth, the iron in blood, The oxygen in every unhurried breath, each was minted in the cores and depths of stars. The same curvature that bends starlight also shapes the slope that time takes through our days. We are brief, yes, but we are built from long-lived things. That may be why the questions won't leave us alone. Black holes and dark matter are not just topics, they're mirrors. What is time when one person's hour is another's minute near a heavy mass? What is information if a horizon can hide it, yet physics insists it cannot be lost? What is awareness if measuring changes what is measured at the smallest scales? These are not riddles for a parlor. They're the pulse in our wrists, answering the pulse in the sky. The more carefully we look, the more we recognize the rhythm. Horizons move. Once they were cliffs at the edge of a flat world. Then they were the orbits of planets, the surfaces of suns, the spirals of galaxies, the ripples frozen into the first light. Now, they are phase transitions in the early minutes, equations that promise a singularity and theories that promise to soften it, spectra that carry the fingerprints of chemistry on worlds we'll never walk, ring-shaped shadows around darkness we cannot touch. Every time the line shifts, the picture of ourselves shifts with it, from center to participant, from spectator to instrument. There's comfort in admitting that we don't want the unknown to end. The unknown is the wind in the sail. It carried canoes across straits and caravans across deserts. It carries questions across centuries. The night is not a void, it's a reflector. Look long enough, and you see not just constellations, but the outline of the questions you brought with you. Each new tool sharpens that outline. A better clock turns gravity into a map. A colder detector hears a lighter particle. A wider baseline resolves a tighter ring. Across all of this, the universe behaves with a dignity that invites trust. Repeat an observation, and the same curve appears. Turn the instrument, and the signal keeps its shape. The lessons have a cadence. Discover gravity, and you are led to curved spacetime. Split the atom, and you are led to fields that never fully sleep. Watch a supernova, and you are led to the origin of the elements that lace through bodies and seas. Hear a gravitational chirp, and you are led to the stiffness of matter at twice nuclear density, and to the way horizons settle after a storm. None of these are endings. They are doors swung open onto other rooms. Light that reaches your eyes tonight may have left its star before apes learned to shape stone. A photon keeps its promise for millions of years and then spends itself on a patch of retina a few hundred microns wide. In that exchange is a gentle truth. We are latecomers with good timing. The universe has been speaking for eons in microwaves left over from its first cool breath, in the narrow lines carved by atoms in starlight, in the red-shifting of galaxies as space stretches, in the long hum of gravitational waves. Yet only now do we own instruments quiet enough to listen without interrupting. Nothing in the record suggests that creation is over. Galaxies will keep braiding and colliding. Stars will keep lighting and going out. Planets will condense from disks and either keep or lose their atmospheres. Black holes will merge and ring. Dark matter will scaffold and guide. The same rules that molded us are still at work in other hands. We aren't living at the end of history, but somewhere interesting in the middle. In a chapter where technology and patience have just become equal to the subtleties the sky offers. Curiosity feels like a luxury until you remember it's how we survived. The urge to see around the bend made fires, compasses, latticed sails, and lenses. It etched maps, and later traced magnetic field lines, and, later still, traced the harmonics in the microwave background. That same instinct now sends detectors to lunar far sides and telescopes to Lagrange points. It trained software to recognize the heartbeat of a pulsar and the whisper of an axion. It stands up in the dark and takes notes. Of course, the truth can be austere. Space is cold, time is unsentimental, stars die, and sometimes worlds end badly. Yet the ledger isn't balanced by absence. For every collapse there is a beginning. For every horizon a light ring. For every silence a spectrum. Even entropy, the slow drift toward uniformity, gives us the arrow that makes stories possible. The rhythm of destruction and renewal isn't an external drumbeat, it's our own. We are born, we grow, we fade. And the narrative does not flatten for that, it widens. When you look up, your questions are not trivial things, and they're not private. They belong in this conversation. They change the kinds of instruments we build, and the kind of care we take with what we think we know. You are not scenery in this play. You are one of the reasons it's more than scenery. A mind made of stardust asks why, and the question is a physical event that moves levers in the world, allocates time on a telescope, sets a budget for a mission, teaches a child to listen for the moment a signal lifts out of noise. That may be the most generous finding of all. The universe isn't mute. It never was. It speaks in our grammar, and it's owned through us when we describe a curve that keeps showing up, and to us, when a new line appears where there wasn't one before. The dialogue runs both ways. Each hypothesis, each model that earns a small green check mark from the sky becomes part of the universe's self-portrait. Each failure that clears the slate makes room for a better likeness. So take this as permission. Keep searching, not for a final theorem that locks every door, but for the next clean measurement, the next careful question that can be asked by two methods and answered the same way. Keep learning the melodies, lensing arcs that betray hidden mass, polarization patterns that remember the last scatter of ancient light, timing residuals that reveal the slow sway of space-time. Keep wondering about the names we have not yet learned to pronounce, phases of matter under crushing cold, new fields that tip the expansion's tempo, surfaces where we expected horizons. The night rewards patience, and it rewards tenderness with data. There is no need to hurry the ending. The point is not to compress wonder into a single formula, but to live in a world where the formulas keep introducing us to new kinds of wonder. We will not run out. The horizon recedes at exactly the pace curiosity learns to walk. Close this evening with a few small scenes tucked behind the eyes, a crescent of light curved by gravity, circling a darkness that is more boundary than thing. A city-sized star ticking like a perfect clock, its beams sweeping past as steady as breath, a halo of invisible matter holding a galaxy's outskirts in a swift embrace. A faint whisper in a detector where two black holes met long ago and far away. A pale planet reflecting a hint of blue-green, its starlight deepened by the breath of a thin sea. None are loud. All are true enough to rest on. In that quiet, notice how the room seems to widen. The ceiling is no ceiling. It's the first page of a book that keeps adding chapters without tearing out the old ones. The questions you carried in here have a place to sit. The answers are not thunderclaps. They arrive like dew, bead by bead,
A soft
enough to shine when the morning
whisper of
tilts.
relief.
Breathe once more, long and easy. The sky will be there when you open your eyes again, patient as always. The story goes on without rush. Curiosity will keep the ink wet. The torches will keep their small circles of light, and the dark, vast, steady, generous will keep humming back, a little softer with each breath, a little farther away, until the room is only the sound of air and the slow turning of the earth, and the last words fold into silence.